Okay, so let's just jump right in. There's this silent arms race happening, like right now, and it's not about what you'd think, not weapons or anything like that. It's all about math. And this race is pretty much going to decide the entire future of our digital security. See, there's a new kind of computer on the horizon, a quantum computer, and it holds the power to basically shatter all the locks that protect, well, everything. We're talking your bank account, government secrets, the whole deal.
And I know what you're thinking. This sounds like something out of a sci-fi movie, right? But it's not. This is the reality that experts are scrambling to prepare for. The entire foundation of our secure digital world, it's about to face its biggest test ever. So let's talk about the lock we have right now. To break the standard encryption we use for a ton of our data today, it's a system called RSA. A regular supercomputer, the fastest we have, would need about 300 trillion years. I mean, just try to wrap your head around that number. It's so big, it's basically forever. And that right there is why we've all felt so safe online. And now here's the key. A powerful quantum computer, sometime in the future, could do the exact same thing in under 8 hours. Think about that. We go from 300 trillion years to less than a workday, from an impossible problem to, well, a pretty easy one. That gap, that absolutely massive gap, that's the whole reason we're talking about this right now. So you gotta ask, how did we get here? And how does this quantum threat actually work? Well, it all comes down to some really clever math that we've been relying on for decades. Math that's about to become, not so clever anymore.
Okay, so the security of pretty much the entire internet is built on this really brilliant idea called asymmetric encryption. The best way to think about it is like a special mailbox. I can give everyone the address and the mail slot, that's my public key. Anyone can use it to drop off a scrambled message for me, but only I have the actual key to open the mailbox and read the message. That's my private key. Super simple, super effective.
The magic trick behind this system is what's called a mathematical trapdoor. It's built on a simple fact. It's super easy for a computer to take two huge prime numbers and multiply them together. That big new number they create, that's the public key. But trying to do the reverse, trying to take that big product and figure out the two original prime numbers you started with, for a regular computer, that's practically impossible. That difficulty, that is the lock.
Okay, and this is the part that's, honestly, it's a little scary. You need to understand that this is not just some far-off future problem. Right now, as we speak, adversaries are doing what's called harvest now, decrypt later. They are literally sucking up and storing huge amounts of our encrypted data today. They're just sitting on it, waiting, because they know that in 5 or 10 or 15 years, they'll have the quantum key to unlock it all. So any data that needs to stay secret for a long time, think government secrets, corporate R&D, your financial records, it's already at risk. So yeah, the race is on. We're in a race to build a whole new kind of digital armor. We need new locks, new encryption, based on math problems that are hard for any kind of computer. Classical, quantum, you name it. And the good news is that effort is already well underway.
In the US, the National Institute of Standards and Technology, everyone just calls them NIST, has been running this huge global competition. You can think of it like a cryptographic bake-off. It started way back in 2017. They invited everyone to submit new algorithms, and for years, the best cryptographers in the world have been trying to break them. Just recently, they announced the first round of winners, and the final standards are expected to be published this year. And that's going to kick off a massive worldwide switchover.
And here they are, the first batch of winners. They've got some cool names, right? Crystals Kyber, Crystals Dilithium, Falcon, and Sphinx Plus. Now, what's really interesting here is that most of these, like Kyber and Dilithium, are based on something called lattice-based cryptography. It's a completely different kind of hard math problem from what we use with RSA.
So how on earth does this new math work? Let's try an analogy. First, just forget everything about prime numbers. Instead, I want you to picture a perfectly organized grid of points, what mathematicians call a lattice. But here's the twist. Don't just think of a flat grid, or even a 3D one. Imagine this grid stretching out to infinity across hundreds of dimensions. I know, it's impossible to actually visualize, but mathematically, it works. Okay, stay with me. Now, imagine we drop you somewhere in this crazy multidimensional space, close to one of the points on our grid. If I give you a good map, which is basically a set of really helpful directions, you could find the nearest point on the grid in a snap. That good map is the private key. But what if I give you a bad map?
The bad map still describes the exact same grid, but the directions are all weird and skewed. With that map, finding the closest point becomes this incredibly hard search problem. That bad map is the public key. And here's the kicker. This problem is hard for everyone. It's hard for regular computers, and it's hard for quantum computers too. All right, so we've got this new, stronger armor. It's based on way more complex math. So logically, your brain probably goes, okay, there's got to be a catch, right? More security, more complex math. It has to be slower. It just has to be. Well, this is where the story gets really, really interesting.
I mean, this is the question that probably keeps network engineers up at night. That little process of establishing a secure connection when you go to a website, the SSL handshake, it's absolutely critical. If these new quantum-safe algorithms make that handshake slow and sluggish, getting anyone to actually use them will be a huge uphill battle. So what does the data actually say?
Okay, first up, let's look at a perfect, sterile lab environment. We're talking ideal conditions, zero interference. And, just like you'd expect, the classic encryption is a little bit faster. Not by much, but it's faster. Okay, no surprises there. The thing is, though, the real internet is never, ever this clean. Now, let's look at the real world, a normal network with all the usual little hiccups like latency and dropped packets, and whoa, suddenly the whole thing flips on its head. The quantum-safe handshake is now faster. It clocks in at 0.23 seconds, while the old stuff takes 0.32 seconds. That's a 28% improvement. How is that even possible?
And this is where it gets absolutely wild. Let's simulate a really messy, congested network. Like when you're on terrible public Wi-Fi. Look at this. The performance gap becomes a canyon. The classic handshake time blows up to 0.77 seconds. But the quantum-safe one, just 0.42 seconds. It's almost twice as fast. We're talking a 45% drop in the time it takes to get that secure connection going. That is incredible. So this is the big takeaway, this totally counterintuitive result. These brand new algorithms, the ones designed to be our future-proof armor, they're not just stronger. They're actually more resilient. They perform better when the going gets tough on the network. That trade-off we all assumed existed, that you have to sacrifice speed for security, it might not even be real. This discovery, this amazing performance boost, it's a game changer. It removes a massive barrier for getting everyone to switch over. It means this whole migration isn't just a necessary security upgrade. It could actually be a performance upgrade too. So with that in mind, what's the path forward for companies and organizations? The big buzzword you're going to hear for the next decade is crypto agility. The days of baking one encryption standard into our systems and then just forgetting about it for 20 years, those days are over. We have to build our technology to be flexible. We need to be able to swap out cryptographic algorithms easily. Think of it like changing a flat tire instead of having to re-engineer the entire car every time. And the roadmap for getting there is actually pretty straightforward. Step 1, you gotta know what you've got. Make a complete inventory of every single place your organization uses cryptography. Step 2, figure out your risk. What data needs to stay secret for 30 years versus, say, 30 minutes? That's how you decide what to protect first. And finally, step 3, plan the migration. Start having conversations with all your vendors, software, hardware, all of them, and ask about their roadmaps for post-quantum crypto, like now. So, here we are. We've come up with the brilliant new math that we need to secure our digital future. The new algorithms are ready to go, and in a crazy twist, they're actually fast. But the greatest shield in the world is totally useless if it just sits on a shelf. The real test, when you get right down to it, wasn't just about inventing the next better lock. The real test is about us. It's about our collective will and ability to actually make the change.